This is one more video in a series where I'm playing around with Mathematica, Wolfram-Cloud, and trying to understand um, the chi-square distribution and sort of chi-square test. And there's a function that sort of goes by that name in Mathematica, Pearson chi-square test. And it's not sort of what I thought it was. I'm not going to sort of explain in detail what it is, but more just show that it's sort of not what I thought it was, not what I wanted here. Okay. So I start off with just a simple simulation of dies, and I made the number of times I'm going to roll the die size and the number of sides of the dice side, so that so then I can change that and sort of see its effect. So there was 900, and I chose 900. It seems a bizarre number, but I wanted in my sort of, my ideal expectations that each side would occur the same amount of time. So I wanted to make my sample size sort of divisible by 6. So that's why the sort of that crazy size of 900. Okay, and then there we are. So I've just established a size and a side, and then I'm just going to use random integer. This is my range, 1 to side, 1 to 6, and I'm going to get size of them. I'm going to get 900 of them, and I'm going to call that list dice. Okay. And then I'm going to generate a table, which is going to, the method table will make me a list. I'm going I from 0 up to size -1, from 0 up to 899, and I'm taking I and taking the modulus, dividing it by side, dividing it by 6, and taking the remainder and adding 1. And that's going to give me 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And so this is going to be my sort of ideal expectation, or this is going to be at least a possible list with an ideal distribution where each one occurs the same number of times as 2, same as 3, etc. And then I'm going to do the count the number of times each die actually occurred. I'm going to call that frequencies, and using bin counts for that. And then I'm going to calculate the ideal frequencies, and that's just going to be a constant array of size divided by side. So that's the value size divided by side, and then they're going to be side of them. Or I could just have done bin counts with my ideal, and that would have given me the same. But this was faster, I believe. Okay, so there we go. Now, when you sort of normally ask, for a chi-square test, you will often be working with frequencies. So I can use my results here, my 148, 145, these numbers, and put them into a chi-squared calculator and see these are my observed values, the 150s are my expected values. Now I ran it and got different values the previous time, but so I could come in here and change these if I want, and then do some calculation. But this is the way that you will find the sort of, like if you test, do chi-square test, and what it will do is evaluate this quantity called the chi-square. It will tell you how many degrees of freedom there were. I had 6 categories, but there was a constraint among the categories that they add up to my number of samples. So there were 5 degrees of freedom. And then it calculates a p-value, which is sort of a probability that what it's so we have this ideal result, and then we make a hypothesis that it is not ideal. Maybe what we're observing is not ideal, not the expected. And then what they call the null hypothesis then is that it is what we expect. And then a p-value is related to sort of should we reject the null hypothesis. And the usual criterion is for p-values less than 5%, 0.05 is a sort of a standard sort of rule of thumb. Like maybe you don't want the null hypothesis. Maybe you want something else. So here we got, the expected makes sense. Then we don't need to reject the null hypothesis. The null hypothesis is that we should expect our expected, and that's telling us that we do. Okay, and these are not quite the numbers that it's random, so they're not the numbers I just wrote. But this is what people mean sort of by chi-square test, and you're usually working with the frequencies. But I want to point out this reference here that what is called Pearson's chi-square test in Mathematica sort of doesn't work this way. So I want to thank this reference that I found here on Mathematica Stack Exchange, that it is not working with frequency data. So the name Pearson chi-square test has led to a bit of confusion for people wanting to count frequency data like these. In other words, it confused me. And in short, I guess that's Mathematica just doesn't have this sort of test built in yet. I don't know when this was done. But anyway, this is not something that you use on frequencies, but that you use on more on the raw data. And then it has some algorithm for working with the raw data. So that is, and I'm just going to show that it doesn't do what I want, rather than figure out what it did do. Okay, so again, you remember I did have raw data. It was called dice, and I have sort of my ideal raw data, which I called ideal. And so then I used the Pearson chi-square test, and it's the data and then the ideal, but again, not the frequencies, but the raw data. And then you can ask for things. So I asked for here the degrees of freedom, and it told me 4. So that already makes me scratch my head. So again, I don't know what it's doing behind the scenes, but my point here is more than it's not what I want. So first, it's not what I want because I was thinking I was working with frequencies. But even if I pointed at the sort of the raw data, it's still not doing what I want, because my degrees of freedom, I think, should be 5, and this is giving me 4. And then it's also giving me a chi-squared and a p-value. So it's in the same, its intentions are the same, but it's not quite what I want. Okay, so then, well, let's do what I want. Okay, so I did calculate frequencies, and I had ideal frequencies. And if I take the difference between my frequencies and ideal frequencies and square that, and divide it by my ideal frequency, that is this chi-squared value. So first I did it down here, just so 18 and 17 are sort of out of order. I wanted to make sure that I was getting the individual things that I thought I was. Okay. So what was my ideal frequency is 150. So I was getting here 148. So 148. So it was 2 over, and then the difference was 2, and then you square that, and that's 4 divided by my 150, and then it reduces it. So that was the 2/75. So that makes sense. That is the what you usually produce when doing a chi-square. Now I'm sort of summing them up, and there I'm getting, and I add an n to make it numerical. Mathematica loves its like rational expressions, and I just want numbers in this case. So I'm taking the frequencies minus the ideal frequencies, squaring that, dividing, scaling that by the ideal frequencies, summing all those up. So there were, in this case, 6 of them, and getting it as a numerical value. So this is my chi squared. And then we're comparing that to, and I have in my previous videos, I sort of got this data and compared it to a chi-square, compared probability density function, a mathematical to a histogram of some data, and that they sort of had a nice agreement. So if you want to see that, look at one of the previous videos. But here I'm switching over to the CDF, the cumulative distribution function for the chi-squared. And chi-squared is parameterized by the degrees of freedom, which was 1 less than the side of my dice. And then the CDF then becomes a function of this value chi-square. And I'm putting in the chi-square particularly for my function. And that gives me some calculation. But this so-called p-value, which is what you use in the test, is actually the sort of the complement of that, or 1 minus that. Okay. And so that is this quantity. So if that were less than 0.05, we would reject the null hypothesis. This is the rule of thumb. We would reject the null hypothesis that we got the expected stuff, and we would say maybe it's something else is going on. All right. So that is the quantity. Let's see, 148, 145. Let's just test this, 148, 145. Can't keep too many things in mind. 158, 144. And 138, 167. I hope I did that right. And then it's telling me what, that my chi was 3747. 3747. And my P is 58.58. 0.58. So this, what I am doing now, is the calculation, at least that I found here on this one site on the internet that does chi-square tests for me. And it is not the same as, it's not even agreeing on the number of degrees of freedom with this Pearson chi-square test that Mathematica provides. Okay, so I have what I want out of Mathematica, just I was thinking that function was what I wanted, and it's not. Okay. Now I just want to go back and like this whole thing was sort of based on the idea that the chi-square distribution mathematically comes from you are taking these normal distributions and you are picking values from a standard normal distribution with a mean of 0 and a standard deviation of 1, and you're picking so many of them, the degrees of freedom, df of them, and taking the value and squaring it and adding and dividing and squaring that and adding those up. Okay, but that is I wanted to see just some behavior of a given frequency. Is my die frequency sort of like that? Is it like pulling from a normal distribution? So here I'm just focusing on the number of times I roll a 1. So I'm just focusing on one of the frequencies. So again, I'm doing this random number between 1 and side, which was 6, and getting, I think this was 900 of them, and I'm asking how many times I got a 1. So I'm doing a count, and I'm counting these things when they meet this criteria. So how many times did I get a 1? And again, our ideal was 150, and we just got 149, so that makes sense. But I can get different things. It is random after all. And so now we want to look at do that a number of times. So I'm going to do, the size was 900, but I'm going to get that distribution. I'm going to get that count. How many times did I roll a 1 in 900 rolls? And I'm going to do that 1,000 times and call that frequency. So I'm making a list of frequencies. So we saw that varied, so I'm going to do it a number of times. And so I've got two, like I'm doing like samples of samples. So I have a sample size of 900, but then I'm repeating that 1,000 times. And that takes a little while, but here they are. So I got, first time when I did 900 rolls, I got 166 times, then 157, then 158, 156, 154. Okay, so we got this. And if we make a histogram, okay, that's looking fairly normal distribution-y. And what else do I want to look at here? I want to look at how, for the frequencies, again, I'm going to just reestablish that my number of sides is 6 for now, but I want to vary that in a minute. So here's what I just did, got all those frequencies. Again, I'm working with just the number of times I roll a 1. So I am rolling the side of the dice I have is a variable. Here I have the number of times I roll as changing. So I'm going to do it for, like, I roll 100 dice, I roll 200 dice, I roll 300 dice. And I'm calculating what I did above, a sort of a set of frequencies, 1,000 of them. And then I'm going to calculate the average and the standard deviation. And then I'm doing that. And then I am scaling it to see how it depends on the size of my sample. So I'll do 100, I'll do 200. Okay. So that's what this did. So I roll the dice so many times and see how many times I get a 1. Then I do that 1,000 times and get that the average and the standard deviation, the sort of spread. And then I am repeating that. So I've got loops upon loops upon loops here. But then I repeat that, and I am changing the number of samples each time. Not the 1,000, but the number of times I roll. Okay. And then I'm just going to, so I have my averages and my standard deviations, and I'm just going to do a quick plot. And this is how this axis is just doing 1, 2, 3, 4, 5, but it's related to the number of samples, sort of. So this was, 1 was really 100 samples, 2 is really 200 samples, but we see that the average scales within. And that makes perfect sense. Then if I have twice as many rolls of the die, then I expect the number of times I roll a 1 to be twice as, if I'm rolling twice as many, the dice twice as many times, then I expect to get a 1 twice as many times. So we expect the average frequency to scale with the size. The standard deviation, the measure of spread, now that might be a little harder to see, but that is more square rooty, and I didn't go through the full fit it to a power, which I should have, but I have not. But let's instead look at take the standard deviation, square, and divide it by the average. And this, you remember, is part of what we were calculating to get this chi-squared. We were taking frequencies minus ideal frequencies, squaring it and dividing by the ideal frequencies. So that is, again, what we are doing here and seeing, and we're going to show one that sort of doesn't depend much on size, but then also see sort of what the value is. Okay, so here is, we've got scatter, but it's scatter. So it seems to have this quantity, this standard deviation squared, or the variance, squared, and the average don't seem to depend much on the sample size. It's just sort of up and down scatter all over the place, and it's hovering around 0.8. And what it is in this case, it seems to be, remember this number, my side of dice was 6, and this seems to be 5/6. So it's hovering around 0.83. Let's see if that is really true by changing. Let's go to 4-sided die, and then run this guy. And then run this guy. And it should still scale as n. This should still, the standard deviation should still scale as the square root. This quantity should still be sort of independent of the size. And now we see it's hovering more around 0.75, because that's 3/4. So I changed the size of the dice, and let's do one more for fun. Let's say a 12-sided die. And then run this. And so the scaling doesn't depend on the side. The frequency scales as n. The standard deviation scales as n to the 1/2. If I get the variance, the square, the standard deviation divided by the average, this should not scale. This should be a constant with n. And now I am up at sort of here, close to 0.9. And that should be, if I'm thinking that it's 1, that's not what I want to do, 11 divided by 12. Okay, so 0.91. So that might be the average now. Okay, so, all right. Let me take this side back to 6. I'm used to thinking about 6. one last thing I want to show. So this, okay, so that was that average, that quantity that we were calculating in our chi-squared distribution tends to be, 5/6 or 3/4 or 7/8 or 11/12, something like that. All right. One more time, I am getting my random dice. I'm doing the bin count, so I'm getting the frequencies. I have my ideal frequencies. I'm calculating my chi-squared. And then I am finding the p-value. So that was 1 minus the cumulative distribution function for the chi-squared distribution with side minus 1, the degrees of freedom, 1 less than the side of the dice, for that value of chi-squared. And I am making an array of p-values. So again, p-value was this, you do this calculation, and then this rule of thumb is if the p-value is less than 0.05, then you might reject the null hypothesis or keep some other hypothesis. But here it's just, we don't have some other hypothesis. It's just about this. Okay, so let's do this. Simulate, simulate, simulate. Takes a little while. Okay. That is a big list of p-values. And now I'm going to, the rule of thumb is if you are less than 0.05. So I'm going to take 0.05 minus the p-value. So if the p-value is greater than 0.5, I'm going to get a negative number. And then the ceiling of it is going to be 0. But if the p-value was less than 0.05, so this is the criterion for the rule of thumb for rejecting the null hypothesis, then I am going to get 0.05 minus the p-value then will be a positive number, and the ceiling of it will be 1. So I'm going to get a bunch of zeros and ones, and my ones will correspond to this suggestion that I should reject the null hypothesis. And so it's mostly zeros, but there's some ones in there. I'm going to be repetitive and do that again, but with the total. And I'm getting, you saw before it was 59, now it's 47. I'm getting of the order of 50 out of my 1,000. So again, this is just what I am expecting here. I made this ideal situation where I know my expected value should be right. And then I'm doing this test, but the test, the rule of thumb is based on sort of 5%. So I expect to sort of, I don't know, a false, and here I expect the null hypothesis to be true. And what it's showing me here is, again, it's a statistical test. So I can expect some false positives. And so I'm expecting false, I'm not rejecting my hypothesis here, but I am getting a false positive that I should reject the null. Maybe it's a false negative. But anyway, I'm getting something false about 5% of the time, which makes some sense that you do expect in statistical tests to sometimes have false positives and false negatives. And here I'm just making it dividing by my 1,000, the number of times I repeated this. But just showing that it's around 5%, which you would expect because your criteria was 5%. So you expect, you might expect false positives at 5%. Now, if the data, if situation where your expectations did not match the things, then you would get, then this would be not false positives, but it may be real, or should occur more than often than 5% of the time or something. All right, that is what I wanted to show you here. Thanks for your attention.